The last application that we're going to look at in this section is going to be the average value of a function. And suppose we have a continuous function f. The average value is essentially going to be, if we added up all the values over a given domain a to b, what would be the average of all of those values within that interval. And suppose to be able to verify or define what the average value formula is, let's just go ahead and partition the function into n heights over the interval from x0 to xn. Then if we added up all those function values and divided it by n, which is our definition of average, it's going to give us our f bar. Okay, now remember, this is an approximation. Okay? Remember that delta x is equal to b minus a over n. And so if we multiplied both sides by n and divided both sides by delta x, we can solve for n as b minus a divided by delta x. And that's exactly what we do right here, is we substitute for n. If we multiply by the reciprocal and clean this up, the delta x becomes a coefficient, as does 1 over b minus a. Now, what we'd like to do is we'd like to take the number of partitions as the number goes toward infinity, all right? And so, of course, that's going to yield our Riemann sum. And so what's going to happen is you're going to get the sum of all of the functions times delta x, all right? So delta x sub I, f at x sub I, limit as n approaches infinity, but this is just the definite integral definition. And so what we really have to find the average value is a really simplistic formula, 1 over b minus a, where b is the terminal point in the interval, a is the initial point, and f of x is going to be the function we're trying to find the average value. Now notice if we multiplied both sides by b minus a, we would get f bar, which is the average value, equals times b minus a equals the integral. And what that basically means is that this would be a rectangle, all right, because f bar is a constant, b minus a is a constant, okay? So this is going to be a rectangle, and it's going to tell us what the area of a rectangle is. And so the area of a rectangle is going to be equal to the area bound by the curve. So this is just the second outcome of the average value, okay? Not that it's all that important, because for most of the examples we're going to be looking at, all I'm going to ask you to do is to be able to find the average value of the function, right? And so just as a diagram, suppose FC is going to be the average value, all right? And we have the point A, we have the point B, all right? And the average value slides somewhere in here, all right? So this is going to be the line, and notice we have a rectangle. And what this rectangle represents is if I add up this area, and this area, okay, and then this area, which is bound by the curve, all right, that's going to be equal to all of this area that's bound under the rectangle, okay? So that's just basically, if you wanted to, another way to compute an integral is to be able to find the average value and then multiply both sides by b minus a. But anyway, let's just take a look at a few examples of average value. All right, so we have our cube root function, and we have the interval from 0 to 8, and we'd like to find the average value. We want to draw a function of the graph and indicate the average value in that graph. Right, so this is pretty easy, right? F bar, which I'm going to call the average value, is 1 over b minus a integral from a to b f of x dx. In this case, b is 8, a is 0. And our function is the cube root of x dx, which is the same thing as x to the 1/3, right? So we can just rewrite that immediately as x to the 1/3 power. And from there, we could just go ahead and integrate right away. All right, so that's not meant to be too difficult. So we're just going to add 1, divide by the new exponent. So we have 1/8 x to the 4/3 divided by 4/3 from 0 to 8. If we multiply by the reciprocal, that's going to give us 3 over 32. And if we substitute 8 back in, we would get 8 to the 4/3. And then if we substitute 0 back in, that's just going to be 0 for us. Okay. When we simplify this, it actually works out really nicely. The cube root of 8 is going to be 2. 2 to the 4th is 16. So we really get 3 to the 2, or 3 over 32 times 16, which is really going to be 3 halves. All right. Now, The other part of the problem says for us to be able to draw a graph of the function, indicate the average value. And I'm going to do two different graphs. I'm going to do one of the graph of the average value, and then another graph of the areas, okay? Because remember, we said if we multiply both sides by b minus a over, and then we multiply it by the average value, that should give us the integral of the function itself, okay, which would be pretty easy for us to compute. Okay, so first graph, okay, and I'm going to use foodplot to help me out. All right, so here's our graph of x to the 1/3, all right, from 0 to 8. All right, so what I did was I just went down here, I changed the x from 0 to 8. And then the other thing I'm going to do is I'm just going to add another function that's a constant of 3/2. Okay. And so this is the average value of the function. Okay, so it just is a line right here that goes right through there. And this area, okay, so I'm going to draw two different graphs just to kind of show you what the average value really can do. Okay, so one of the graphs is just going to be this, okay, where this is the line y equals 3/2, okay, and then this is going to be the point 8, 2. And so this would be the area bound by just the function itself. Okay, so, and I'm going to call that A1. All right. Now, if I were to graph just the average value, okay, I'm going to do that with a different color. And again, this is just so you guys can understand the average value of the area part of the average value. Okay, so there's a function again, and then here's that line. Okay, a little bit closer, but again, okay, this is going to be the point 8, 2. All right, and I'm going to call this A2, and that's going to be the area bound by the rectangle. Okay, and the average value by multiplying both sides suggests that A1 is going to be equal to A2. And so realistically, what we could say, just to illustrate this, is that, remember we got 3/2 was f bar, and b minus a is 8 minus 0, which is 8. Okay, so check this out. This is really cool. All right, so when we go through, we know that b minus a times f bar, not f prime, but f bar, is going to be equal to 8 times 3/2, which is going to be 12. Now check this out. Remember, we said that this is going to be the same as the integral from a to b of f of x dx, which is going to be integral 0 to 8 of x to the 1/3 dx. And we should get 12 out of that. So that's going to be x to the 4/3 divided by 4/3 from 0 to 8, which is the same thing as 3/4 times 8 to the 4/3 minus 0. And we know that 8 to the 4/3 is going to be 16. All right, so that's going to be 3/4 times 16, which is going to be 48/4, which is 12. All right, so notice that the areas, okay, and notice that this was a little bit easier for us to compute than going through and doing the integral. All right, so this is equal to 12 square units, and then this area is also equal to 12 square units. All right, so that's basically a couple interpretations of the average value. Okay, so remember, average value is if you added up all the possible values that lie on this function, okay, that's what the sum or the average of those would be. But also there's a secondary area definition. And then finally, we can also use that area to help us to evaluate definite integral, okay, if we know what the average value is. All right, so for the rest of this section, we're just going to take a look at a couple more examples of average value.